Hi everyone! So this will be a series of videos about infinite sequence covering the following topics: definition and examples of infinite sequence, limit of an infinite sequence, and monotonic and bounded sequence. If this is the first time you're watching this video, don't forget to click the subscribe button to get updated with my latest lesson. At the end of the lesson, the students are expected to be able to define an infinite sequence, write the terms of a sequence, write the formula for the general term of a sequence, determine whether a sequence is convergent or divergent, find the limits of a convergent sequence, determine whether a sequence is increasing or decreasing, and understand and apply the bounded monotone sequence theorem. So let's start with the definition and examples of infinite sequence. An infinite sequence, or simply a sequence, can be thought of as an unending list of numbers written in a definite order. We have A1, A2, A3, A4, and so on, or in general AN, where A1 is called the first term, A2 is called the second term, A3 the third term, and so on and so forth, or in general, A sub n is called the nth term of the sequence. Mathematically, we define a sequence as the range of a function whose domain is the set of positive integers. If f is a function, then the corresponding sequence is given by the values of the function evaluated at the set of natural numbers. We have a1 equals f of 1, a2 equals f of 2, and so on and so forth, or in general, an is equal to fn. An is called the general term of the sequence, so f of n is the formula for the general term of the sequence. In this manner, we can also write the sequence enclosed by open and close parentheses, or since we can write the general term of the sequence as f of n, then we have the sequence fn n from 1 to infinity. If the values of n are clear, then we can remove the subscript n equals 1 up to and the superscript infinity, and just do away with open and close parentheses, then write the general formula or the formula for the general term of the sequence f of n. Let's have some examples. Let's give the dividing formula, then write the first few terms of the following sequence. The first sequence is n over n plus 1, n from 1 to infinity. The second sequence is negative 1 to the n, quantity n plus 1 all over 3 to the n from 0 to infinity. And the third sequence is square root of n minus 3, n from 3 to infinity. So we want to write the terms of the sequence using the general formula. So for number 1, the general formula is given by an equals n over n plus 1. Since n starts with 1, so all we need to do is to write the value of the formula or evaluate the value of the formula using n equals 1. So that's 1 half. Next is n equals 2. So that's 1 or 2 over 3. Next is 3 over 4. Next is 4 over 5 and so on. So you already have an idea of the next term. So that's your sequence. For the second sequence, the formula is given by an equals negative 1 to the n plus 1 over 3 to the n. N starts from 0 up to infinity. So we just evaluate the formula starting with 0. So we substitute 0, negative 1 to the 0 gives me 1, 0 plus 1 is 1, 3 to the 0 is 1, so that's 1. Negative 1 to the 1 is negative 1. 1 plus 1 is 2. And then we have 3 to the 1. So 2 over 3. So I have negative 2 over 3. N equals 3. So n equals 2 rather. So we start with 0. So this is n equals 0. This is n equals 1. So n equals 2. Negative 1 to the 2 is positive. N plus 1 is 3. 3 to the 2 is 9. But if we simplify it, we have 1/3. Next, n equals 3. So negative 1 to 3, that gives us a negative value 4 over, so that's negative 4 over 3 cubed, 27. Next value is n equals 4, so that's positive 5 over, so that's 3 to the 4 or 9 times 9, 81. And so on and so forth. So you already have an idea or the pattern of the sequence. Next, the general term is given by square root of n minus 3. We are starting from n equals 3 up to infinity. So we start with 3, 3 minus 3, 0, square root of 0 is 0. 4 minus 3 is 1, square root of 1 is 1. 5 minus 3 is 2, so square root of 2. Square root of 3. Square root of 4 is 2. Square root of 5. Square root of 6, and so on. And you have the general idea of the next term. So that's how you write the terms of a sequence. You simply plug in the set of natural numbers on the formula of the general term. Of course, we need to identify in what particular value we are going to start. And usually it's indicated by the subscript n equals. So for number 1, it's n equals 1. For number 2, it's n equals 0. For number 3, it's n equals 3. But if there is no subscript indicated, then automatic we agree that it starts with n equals 1. Okay, so now let's see if you can do it on your own. Get your pen, get your paper, and do the self-check test number 1. Pause this video for now and we'll get back with the answer later. So, did you do it? Very good. So, here are the answer. Check if you got the correct answer. Now, there are cases when a sequence exhibit a particular behavior or pattern that is easy to recognize. And we should be able to easily identify what particular sequence a series is by examining the pattern of the sequence. Here is a typical example. An arithmetic sequence is a sequence in which the difference between any two consecutive terms is a constant. That means if we get the difference between and an minus 1 or the preceding term, we get a common difference. So let's denote this common difference by D. So we can write A2 as A1 plus D, A3 as A2 plus D, but since A2 is A1 plus D, then we can rewrite this A2 as A1 plus D. So we have A1 plus D or A1 plus 2D. So we can write A3 as A1 plus 2D. Now A4 is A3 plus D. Again, A3 is simply A1 plus 2D. So if we plug in this value here, then we get A1 plus 2D plus D or A1 plus 3D. Now, the pattern is already obvious. If we want to get the general term, so for example, let's say A5, we want to get A5. So A5 is simply A4 plus D. But again, A4 is A1 plus 3D. So that gives us a formula for A5, which is A1 plus 4D. So if the subscript is 2, then the formula is A1 plus 1D. If the subscript is 3, then the formula is A1 again, plus this time it's 2D. From 3, it's now 2D. If the subscript is 4, then the formula is A1 plus, well, you guess it right, 4 minus 1. So that gives us 3. So if the subscript is 5, what do you think is the formula? Correct, A1 plus 4D. In general, if you have A sub n, so the formula for A sub n is, very good, A1 plus quantity n minus 1D. So because of the pattern, because of identifying the pattern, we're able to establish a formula for the general term. So this is now the general term for an arithmetic sequence, A1 plus n minus 1D, where n denote the position on the sequence. So the nth term is given by A1 plus n minus 1D. Another typical pattern in a sequence is geometric. A geometric sequence is a sequence in which the ratio of every two successive terms is a constant. So that means if we divide the two successive terms AR and AR minus 1, we get a common ratio. So let's denote the common ratio by R. So R is equal to AN over AN minus 1, or the two consecutive term of the sequence. So from here, we can write A2 as A1 times R. Now A3 is derived by multiplying the second term by R. But since A2 is A1 times R, then we can rewrite this as A1 times R or A1 squared. A4 is derived by multiplying A3 with R. Again, A3 is A1 R squared. So we have A1 R cubed. Can you guess the next term? So what is A to the 5? A to the 5 is A4 times R. But A4 is A3 A1 rather R cubed. First term times R cubed. So how do you get R cubed? 4 minus 1, yes. So now we have A5. A5 is A1 times R to the 4. Very good. So in general, we can get the formula for AN. So AN is simply, so look at the pattern. If the subscript is 4, that's A1 times R to the 4 minus 1. If the subscript is 5, that's A1 R to the 5 minus 1. So in general, we have AN equals A1 times R to the N minus 1. Very good. So that's called a geometric sequence. The next term is derived by multiplying the preceding term by the common ratio R. But because of the pattern, we're able to identify the formula for the general term. So the formula for the general term of a geometric sequence is given by A1 R to the N minus 1, where N minus 1 is the position of the, where N rather is the position of the term. Another typical pattern is a harmonic sequence. Harmonic sequence is a sequence whose reciprocal of each term form an arithmetic sequence. So if you get the reciprocal of each term, then what you get is a harmonic, rather an arithmetic sequence. So that means AN is a harmonic sequence if and only if the sequence 1 over AN forms an arithmetic sequence. Okay, so let's try some example. Let's find a formula for the general term AN of the given sequence, assuming that the pattern of the first few terms continues. So the first sequence is given by 2 over 3, 4 over 3, 2, 8 over 3, 10 over 3, and 4. The second sequence, 3 over 5, negative 4 over 25, 5 over 1 to 5, negative 6 over 6 to 5, 7 over 3, 1 to 5. Number 3, 1 half, 1 fifth, 1 eighth, 1 11, 1 over 14, and so on and so forth. Number 4, 1/2, negative 4 over 3, 9 over 4, negative 16 over 5, 25 over 6, and so on and so forth. We want to determine the general term of the sequence, and we can do this by examining the pattern exhibited by the first few terms of the sequence. So let's look at the first example. The first term is 2 over 3 and the next term is 4 over 3. So there are a lot of ways to get 4 over 3 from 2 over 3. You can multiply stuff, you can add stuff, but the next few terms will give us a determinate way to determine the formula. For example, if we try to say multiply 2 to get 4 over 3, so we get 2 thirds times 2 is 4 thirds, but 4 thirds times 2 is 8 thirds, and that's not equal to 2. Thus, the next term, the third term is 2 and not 8 thirds. So that means that multiplying by 2 is not the correct pattern. Let's try addition. So what do we need to add to 2 thirds to get 4 thirds? Of course, that's 2 over 3. So if we try to add 2 over 3, so we get 4 over 3. Now, if we try to add another 2 over 3 to 4 thirds, we get 4 plus 2, that's 6 over 3, which is equal to 2. So we get the correct pattern. We need to add 2 over 3 to each term. Let's try to look at the next term if it will give us the correct answer. 2 plus 2 over 3, or that's 6 over 3, plus 2 over 3 is 8 over 3, so that's correct. Plus 2 over 3 gives us 10 over 3, so that's correct. Plus 2 over 3 again is 12 over 3, which is 4. So we got the correct pattern. So the pattern is adding 2 over 3 from the previous term to get the next term. So that means this is a, or rather an, arithmetic sequence where the common difference is 2 over 3. So what's the formula for the general term of an arithmetic sequence? The formula for the general term is given by first term plus n minus 1 d. Having that in mind, we have an equals, the first term is 2 over 3 plus n minus 1 quantity 2 over 3. Or if we simplify that, we have 2 over 3 plus 2n over 3 minus 2 over 3. Or that's simply, we can cancel 2 over 3, 2n over 3. So that's the formula for the general term. To check, let's say we have the sixth term. 1, 2, 3, 4, 5, 6. So that's 2 times 6 is 12 divided by 3, 4, which is correct. Okay. For the second term, or second sequence rather, we have the following terms. We have 3 over 5, negative 4 over 25, 5 over 25. So this is a little bit trickier than the first one. So, if we look at the pattern, we cannot particularly find a particular value, or we can add or multiply the whole term of the sequence to get the next term. But if we look at it separately, the numerator and the denominator alone, looking at the numerator, it's easy to figure out that the numerator exhibit an obvious pattern. 3, 4, 5, 6, 7. It's an arithmetic sequence. If we disregard the algebraic sign, positive or negative, we have an arithmetic sequence. 3, 4, 5, 6, 7. So this is the first term. So the first term is 3. This is the second term. So you get the next term by just adding 1. So the numerator is determined by adding 1 plus 1. Again, we're disregarding the algebraic sign first. How about the denominator? If we look at the, maybe I need to put the arrow on top rather than the bottom. So let's put the arrow on top. Okay. So if we add 1 to the numerator, disregarding the sign, we get the next term. Right? So the numerator is following an arithmetic sequence where the common difference is 1. Again, we are, take note, disregarding the sign. We'll deal with the sign later. On the other hand, the denominator follows also an obvious pattern. 5, 25. So to get 25, you simply, can you guess what the pattern is? Yes, you multiply it by 5. Because if we look at 25, if you multiply it by 5, you get 125. Again, if you multiply it again by 5, you get 120, 625 rather, and so on and so forth. So the denominator alone exhibits a geometric pattern. So how do you get the numerator? The first term is given by n plus 2, where n is equal to 1. Right? For the second term, n plus 2, 2 plus 2 is 4. For the third term, 3 plus 2 is 5. So the formula for the numerator is n plus 2. How about the denominator? The formula for the denominator is 5 to the, this is 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 4, 5 to the n. Now, how do we rectify the algebraic sign, the positive and the negative? You do that by multiplying a term negative 1 to the n. But if, remember, this is n equals 1, this is n equals 1, this is n equals 2, this is n equals 3. So if n equals 1, negative 1 to the n, negative 1 to the 1 is negative. But we need a positive number here. So what do? You subtract it by 1. So negative 1 to the n is 1, 1 minus 1 is 0, negative 1 to the 0 is positive. So now the negative 1 terms agrees with the first term. Negative 1 to the 0 is positive, and this is positive. Negative 1 to the 2 minus 1 for the second term, 2 minus 1 is 1, negative. For the third term, 3 minus 1 is 2, negative 1 to the 2 is positive, and we have a positive term here. And so on and so forth. So if you have an alternating sign, if you have alternating positive, negative, positive, negative, positive, all you need to do is to multiply either. So you choose from negative 1 to the n or negative 1 to the n minus 1, depending on the first term. So depending on the value of n, if n is equal to 1, then this is negative and this is positive. If n is equal to 2, then this term here will become positive and this term here will become negative. If n is equal to 3, this term here will become negative. So it will alternate and this term will be positive. So if negative 1 to the n starts at n equals 1, then the terms will be negative, positive, negative. On the other hand, if you use negative 1 to the n minus 1, starting from n equals 1, the terms will be positive, negative, positive. So you decide which one agrees with the terms. So since the terms are positive, negative, so you use negative 1 to the n minus 1. So we were able to find the pattern if we split it. We look at it as at the numerator first, and then we look at the denominator, and see the pattern and combine all of them in one single formula. So we now have the formula for AN. Just to check, let's see. Let's say we check fourth term. We check at the fourth term. So the fourth term, if we use 4, 4 minus 1 is 3. Negative 1 to the 3 is negative. So it's correct, negative. 4 plus 2 is 6, correct. 5 to the 4 is 25 times 25, 625. So that's correct. So indeed, this is the general term for the sequence. Now, for number 3, the terms are given by 1 half, 1 fifth, 1 eighth, 1/11. Well, if you look at the denominator, they exhibit a common pattern. 2 plus 5, or rather 2 plus 3 is 5. 5 plus 8, or rather 5 plus 3 is 8. 11 minus 8 is 3. 14 minus 11 is 3. So that means we have a common difference in the denominator, d equals 3. If we get the reciprocal, we get an arithmetic sequence. 2, 5, 8, 11. So what do you call this kind of sequence? The first sequence, what do you call this kind of sequence? Yes, harmonic sequence. So what's the pattern for the arithmetic sequence? The arithmetic sequence is the reciprocal. So the reciprocal is an arithmetic sequence with a common difference, d. So the general term of the arithmetic sequence is given by first term plus n minus 1 d. Or plugging in the value of the first term, that's 2 plus n minus 1, d is 3. So to simplify, that's 2 plus n minus, plus 3n rather, minus 3. Or that's equal to 3n minus 1. This is the formula for the general term of the arithmetic sequence. Remember, this is the reciprocal. So this is an arithmetic sequence. So what is the general term for the harmonic sequence? So we get the reciprocal to go back to the original harmonic sequence. So for this sequence, the general term is given by the reciprocal of this. So that's equal to 1 over 3n minus 1. And that's the general term of the harmonic sequence. Okay? Okay, for the next example, so we have 1 half, negative 4 thirds, 9 fourths, negative 16 over 5. Okay. So, again, we immediately see the denominator and the numerator has different pattern. For the denominator, it's easy to see that it's an arithmetic sequence, right? Because for the denominator, the common difference is 1 plus 1 plus 1. You just subtract the next term from the preceding term. So 3 minus 2 is 1, 4 minus 3, 5 minus 4 plus 1. So the common difference is 1. So the denominator is given by n plus 1 because the first term is 2 and you add 1 every time. So this is first term, 1 plus 1. Second term, 2 plus 1, 3. Third term, 3 plus 1, 4. How about the numerator? The numerator has an interesting pattern. Again, it's positive, negative, positive, negative. So what do we multiply if we have an alternating positive and negative terms? The first term is positive. So we're already sure that it should be negative 1 to the something. So either it's negative 1 to the n or negative 1 to the n plus 1 or n minus 1 rather. So if you want the first term to be positive and n starts with 1, so 1, negative 1 to the 1 is negative, so we need to subtract 1. So that should be n minus 1 to the exponent. So that it becomes 1 minus 1 is 0, negative 1 to the 0 is positive. So the first term is positive. Now, the 1, the 4, the 9. What's the pattern? 1, 4, 9, 16, 25. It's not multiplying by 4 because if I multiply the first term by 4, the next term cannot be derived from multiplying 4. 4 times 4 is 9. It's not adding 4. Because if I add, this is 4 minus 1, 3. But this is 9 minus 4, 5. So, it's not an arithmetic sequence. It's actually a sequence of special group of numbers. Look at this one. 1 squared is 1. 2 squared is 4. 3 squared is 9. And so on and so forth. So do you get the pattern now? Yes, that's the square of the position of the term. So if it's on the first position, if it's the first term, you square 1. The second term, you square 2. The third term, you square 3. And so on and so forth. So it's the position n raised to 2. N squared. Let's check. This is 1, 2, 3, 4, fifth position. Let's check out the fifth position. This is negative 1 to the 5 minus 1 is 4. So that's positive, correct? N squared, 5 squared is 25, correct? 5 plus 1, 6, correct? So this is the general term of the sequence. Okay? So all you need to do is to figure out the pattern being exhibited by the first few terms of the sequence. Well, assuming that that pattern will continue to the rest of the terms of the sequence. Okay, so that's how you get pattern for a sequence. Now let's see if you can do it on your own. Get your pen, get your paper, and do self-check test number 2. You just have to determine the formula for the general term. You figure out if it's an arithmetic sequence or if it's a geometric sequence or a harmonic sequence or a combination or a particular pattern arises from the first few terms. And then write the general term or the formula for the general term AN. Okay, so pause this video for now and we'll get back for the answer. Did you do it? Were you able to get the formula for the general term? So to check if your answers are correct, for the next video, we're going to discuss limit of an infinite sequence. For now, just keep on practicing writing the general term of an infinite sequence. See you next time!